Hello everyone. This is the second video of 3 and it's on the cylindrical coordinate system, whereas the first one was on the Cartesian coordinate system. So what I'm going to do with this is I'm going to take this coordinate system that I've already drawn, the XYZ system. I've made sure that it meets the right hand rule. So again, the right hand rule, remember, requires that when I'm holding my right hand, this right finger, index finger, has to point in the X direction. This right finger at 90-degree angle has to point in the Y direction. And then when you have that, the right thumb points in the direction of the positive Z axis. So the positive X axis, positive Z axis, and positive X axis, positive Y axis, and positive Z axis. So I've made sure that's the case. Now I'm going to show you the unit vectors, which you see will be a quite different thing than I hat. These actually move with the point in question, and they're actually going to be functions of the position. So unlike with Cartesian coordinates, when you do an integral or a derivative of a vector in Cartesian coordinate systems, you don't have to take the integral or the derivative of the I hat, the j hat, or the k hat specifically because those vectors are constant. These vectors, however, are functions of variables, and you'll see that they're in fact functions of x's, or you can even make them functions of theta. Actually, the way I'll derive it comes up with functions of theta. So we'll go with it and start here. So this is the cylindrical coordinate system, which is just like polar coordinate systems, if you've ever learned those, but it's polar coordinate with a z-axis. So everything else is just like polar, other than the fact that it has a z-axis. So let me go back to my document cam. Now what I'm going to do is I'm going to try to use a ruler as much as possible just to make sure the drawings come out nice and neat. I also don't want it quite so blurry, but I don't know why it keeps coming blurry. Let's see if I can get this word up there. Maybe that should be enough for it to focus on. There you go. That looks a lot better to me. So if we imagine a point in space, say right here, okay, that point could be given the coordinates. I'll call that point P. That point could be given the coordinates X, Y, and Z. But we're going to make up another coordinate system where we're going to say that coordinate or that point has the coordinates of R, theta, Z. Obviously, the Z is not going to change, but the R and theta are going to be quite a bit different. So how do we do it? Well, first off, we imagine a projection of this point down into the XY plane. So I draw this down here and say I'm down in the XY plane now. And then I draw a line from the coordinate origin to that point, but staying in the XY plane. So this distance right here, from here to here, is the variable r, which I shall draw in red. Okay. Now, additionally, this angle here, theta, sweeps out counterclockwise as seen from the positive z-axis, counterclockwise from the positive x-axis. So you're looking down along the positive z-axis, and you're looking at the positive x-axis, and it rotates counterclockwise. So that's our second variable. And then, of course, our third variable is the z. Okay. Now, we've sort of established what the coordinates are. Now I need to talk about what the actual unit vectors and stuff like that are. So first off, let's not only that, we also sort of need to have some equations for converting back and forth, all that sort of stuff. So let's look for a second. I'm going to place this in the XY plane so we know where this point is. It appears this should be right about here. So that's the point X, if you will, or that's the X coordinate, if you will. Now the Y coordinate should be followed back parallel to the X axis like this, and that will be my Y value. And I think you can see from that that R is equal to the square root of x squared plus y squared. So that's how you get R from an X and Y coordinate system. Okay, that's a really horribly drawn thing, but I think you see what I'm trying to say here. That's r is equal to square root of x squared plus y squared, because you can see this is just a triangle, x squared, y squared, and that, of course, is the hypotenuse of the triangle. Of course, z is just equal to z, and we could also figure out what theta will be. I think you can tell that theta would be the tangent inverse of this value over that value, and this value is the y, so it'd be y over x. So, and of course, z is z. So that's the way you can convert to r theta and z from x, y, z. Later, I'll give you some stuff to help you figure out how to get from r theta and z to back to x and y and z. Okay. Now, we also want to talk about what happens if I decide to vary this a little bit. Maybe I want this to be, maybe I want to make a surface area, for instance. So maybe I consider varying r, and let's say now instead of r being this whole length, well, no, I don't want to mess that. I'll do like this. I'll say r, and I'll extend it just a little further than r automatically already was. I'm extending it by an amount dz, or excuse me, dr. Okay. Now I'm also going to extend theta by an amount d theta. So for that one, I'm going to draw like this. And I think you'll see that this makes a little arc right here. And this makes a little arc right here. So what I've done is went from r to r plus dr. So this distance right here is dr. And what theta did was theta went from theta to theta plus d theta. But that's the angle. I need the actual dimension to make that an area element. So the actual dimension, if you happen to remember, S is equal to R times theta, the formula for arc length and sort of the definition of radians. S is equal to R times theta says that this little S right here is just R d theta. Okay? So we can assume that this area is just roughly R d theta, or I'll do it like this. dA, and this will be r theta vector. Again, I got to put a plus or minus because there's no convention on which way you should draw the point, but we know it's perpendicular to this. So it's actually equal to r d theta times dr. So I'm going to write it as r dr d theta, and it points in the plus or minus k hat direction. So that's my first area element. Okay, that's by varying r and theta. Okay, hopefully I can see that well enough. Maybe I should stop writing in the blue, except for maybe drawings, but the symbols don't come out too good. And also I'll raise this up so you can see it a little better. So dA is equal to r d theta. Okay, and that's because this is r d theta right here. So that gives us roughly the area of that sort of rectangular shape. You can tell it's actually got an arc on it, so it's not that. If you actually wanted to work it out, you could work it out, and what you'd find out is the difference between this and an actual rectangle is of the order of dr squareds and d theta squareds and dr times d theta and stuff like that. So you would actually find out that this is quite accurate because we're going to end up integrating and taking the limit as dr approaches 0 and this d theta approaches 0. So in the end, those quadratic terms really don't come out at all, so you don't have to worry about that. Now, what about if we wanted to let r vary and z vary? Well, that's easy enough. Now we're going to go up here and draw another coordinate. So I'm going to go up here and draw straight from this corner up this way. I'm trying to estimate roughly how far I should draw it, but I'm not going to do it perfectly probably. So now I take this parallel to here and see that this could be, for instance, z, and then of course dz would be a little bit higher than that. So I go a little bit higher than that. So this amount way up here would be dz. That would make this little rectangular area. Now this one is actually really a rectangle, so we're not losing any, we're not even having to rely on the infinite sum and stuff like that. This one in fact is going to be called dA sub ZR, or I'll say RZ. And of course, it's got to have the plus or minus again, as I've said many, many times. But you can tell this dimension is dz, this dimension is dr. So I'm going to say dr dz. And of course, they point in a weird direction. It's called the theta hat direction, and I'll draw that in a second to help you understand what that is. It actually points in the direction of increasing theta, so it has to be perpendicular to this r. And the next one, of course, we're going to draw is going to be defined in terms of the r hat direction. And that's going to be what happens when you let theta vary and z vary. So if you let theta vary and z vary, what you end up getting is this, and I can make it a little neater by using my rulers. So this amount right here would be r d theta, and of course this amount right here would be just dz. So that's a different area. I drew this one a second ago for that. This area right here would be dA, and this one was changing theta and z. So I'll say dA sub theta z vector, plus or minus. Now in this case, this length is r d theta, and this length is dz. So I'm going to say r d theta dz, and it points in that weird direction r hat, which I'm getting ready to work out for you. Okay. So now we've got our differential area elements. I think you can realize by putting them all together, if I drew this line up, then what I'd end up getting, and of course trace this line out as well. So let me give you a rough estimate of what that looks like. Come here like this, do that, come from here to here, do that, do this. Now you see I get a little rectangular solid that actually has an arc on this end and this end, so it's not technically an arc. But in that case, you can get a volume element, and dV for that happens to be r dr d theta dz. So that's another thing we can use. In fact, we could integrate that all by itself and determine the volume of a cylinder with no integrand whatsoever. You're just using the dV. So that's kind of nice. Now we've got the dAs, we've got the dV. Now all I need to do is work out the actual unit vectors. So what I'll do is I'll use my black marker and realize that, or black pen, and remind you that r hat will point in the direction of increasing r, just like I hat pointed in the direction of increasing x, and y hat pointed in the direction of increasing y, so on and so forth. So what I'm going to say is this is in the xy plane, and I'm drawing it quite a bit bigger than it really is, probably. Okay, that vector right there is going to be called r hat, and again, the hats mean that it is a 1 unit long. I'm going to work it out as if I'm going to have to change it to 1 unit, but that's because I know what the results will be. So that's r hat, and then you can tell from this, tracing the y-axis over to, or I mean the x-axis over to here, you can tell that in fact this angle right here is theta, and this is in the xy plane. So you know the y coordinate is parallel to the y-axis, or the y component is parallel to the y-axis, and you know the x component, of course, is parallel to the x-axis. And I think you can tell that since this is theta, this is a right triangle because this is the x-axis and this is the y-axis, so they're clearly perpendicular. So if I did sine of theta, it would be y over hypotenuse, which would be r, but r is just 1. So sine theta equals y over 1. Similarly, cosine theta Cosine theta is adjacent over hypotenuse, so that's x over the hypotenuse, which again is 1. So I now know the magnitudes of the components of the x component and the y component. So what I'm going to say is r hat, dang it, I wrote it as r vector. R hat is equal to the x component. Notice it's in the positive x direction, that's in the positive y direction, so I just write it down automatically. Cosine theta I hat plus sine theta j hat, and that is your actual r hat vector. Now the theta hat vector also lies in the xy plane, but it is in fact 90 degrees ahead because it points in the direction of increasing theta. So if I wish to draw that, I'm going to have to draw it perpendicular to this guy. So I'm going to say roughly like this. And again, I'm going to try to make it big. So that's my theta hat vector. Again, these are just unit vectors like I, j, and k, but as you can tell, this one is a function of theta, and therefore it's also a function of x and y if you're integrating with respect to x and y, because cosine theta is clearly x over square root of x squared plus y squared, and sine theta is clearly y over square root of x squared plus y squared. So now theta hat, I can try to work it out. I'm going to write it right here, but I think what you'll see is if I draw the x-axis continued this way, what I see is the angle between the x-axis, I said the x-axis, but parallel to the y-axis is what I meant. If I realize that the direction of the x-axis and the direction of the y-axis are 90 degrees from each other, and that I move this theta degrees ahead of the x-axis, and this is 90 degrees ahead of that, then that tells me immediately that this angle is also theta. So I can actually get the x and y components, if you will, of theta hat. So the y component of theta hat is going to be parallel to the y-axis, to the x-axis. So I draw it just like this. And that's the actual x component right there. And then the y component will be right here. The main thing I'm wanting to stress about drawing these right now is that you see the x component is actually in the negative direction, and the y component, x component is in the negative direction, and the y component is in the positive direction. So I've got to add that sign to make my theta, my formula for theta hat work. I haven't addressed whether this is a unit vector yet, but I'll show you that in a second. So now this is the y component. Notice that's parallel to the y-axis, and that y component would be given by cosine of theta, because we can see cosine theta here is equal to adjacent over hypotenuse. We're going to assume theta hat is 1 again. So in this case, cosine theta is in fact y over 1, and sine theta, on the other hand, ignoring the sign, the actual plus or minus sign, is equal to opposite, which is the negative of the x direction, over 1. So in this case, I'm going to say theta hat is actually equal to negative, because it did point in the negative x hat direction, or in the negative x direction. So it's negative sine theta I hat plus cosine theta j hat. And of course, the obvious is true. Z hat could equal K hat, or K hat could equal K hat, whatever you want to call it, it's just fine. So these are your unit vectors in the in the cylindrical coordinate system. If you ever forget it and you can't motivate this drawing and derive it yourself, then all you have to do is come up with cosine and sine. That's sort of like every vector, right? When you first learn it, when they're trying to teach you how to do vectors in kindergarten, if you will, they're wanting you to blindly take theta as measured from the counterclockwise from the positive x-axis being positive, or if you're going clockwise, then it'd be, of course, negative. And then you could blindly say the cosine theta automatically gives you x over the magnitude, and the sine theta gives you y over the magnitude. So r is just like a regular vector. But if you take the derivative of this, you'll see that you actually get theta hat. So if you forget this derivation, you can still come up with it just by taking the derivative. Derivative of cosine is negative sine. Derivative of sine is cosine. So that's why you get, that's how another way you can get theta hat. Theta hat is the instantaneous rate of change. I shouldn't say instantaneous because I'm not taking derivative with respect to time, but it is in some sense an instantaneous rate of change of the r hat. So anyways, now the last thing I think I should do here is not necessarily take the time to try to use the differential area elements, but let's by all means take the time to calculate the actual volume of a cylinder. So if we imagined a cylinder that was in the coordinate system, I'm going to draw the whole coordinate system over again, just really small. So this is X, this is Y, and this is Z. Let's imagine a cylinder centered on the Z-axis. In other words, its rotation axis is the Z-axis. So this would generally be the shape of it. And of course, it goes up this way and this way. And that would be our cylinder. So let's say the radius of the cylinder is big R. And let's say the height of the cylinder is H. So the integral, or the volume of the cylinder, is equal to the integral of dV, which is that thing I just calculated. So I'm going to say the integral, and I'm going to do it in this order. I'm going from last to first. So Z is going to go from 0 to H. Theta is going to have to go through a whole 2 pi degree, or 2 pi radians. And then finally, the very first integral we do will be R, and R is going to go from 0 to big R. And the integral of dV is just the integral of R dr d theta dz. So first off, the integral of r dr is just 1/2 r squared. So I get 1/2 r squared for that one. Notice I went ahead and plugged in r equals, little r equals big R, and little r equals 0, but the little r being equal to 0 gave us no term whatsoever, so I just got left with 1/2 r squared. Now I have the integral from theta equals 0 to 2 pi of the integral, oh, excuse me, I left the integral out here. I flipped the order. That's z equals 0 to h. That's what it should be, and we'll leave that off. Now I have the integral of d theta dz. Again, sorry about that little squiggly. That says d theta, that says dz. Actually, let's scribble the whole thing and just say d theta dz. Now, the integral of d theta is just theta, but that's evaluated at 2 pi and then evaluated at 0, so you get 2 pi minus 0. So I now have 1/2 r squared times 2 pi minus 0 times the integral from z equals 0 to h of dz. So now I have, notice the 1/2 and the 2 cancel one another out. So I have pi r squared. The integral of dz is just z, and then I'm going to evaluate that from z equals h minus z equals 0. So ultimately my formula is the volume of a cylinder is pi r squared h. So you can see how immediately useful that triple integral process and those differential area, volume elements, that sort of thing. You can see how they became useful. Of course, we didn't do anything with the dAs at this point, but we did do something with the dV. Now, the last part that I was supposed to give you was a way to go from R to, in fact, X's and Y's. So we already have going from X and Y to actual R, theta, and Z. So the other way around, we can realize that theta is equal to the inverse tangent of y over x. So we can do that and just say, oh, well, if I want to know x, x is equal to r times cosine theta. If I want to know y, y is equal to r sine theta. And if I want to know z, z is just equal to z. So those are the transformation equations to transform from xyz to r theta z. And now here's the ones to transform from r theta z to xyz. So that's all you pretty much need to know about the coordinate system. Just knowing these vectors exist gives you a language and vectors to use in your Gauss's law, for instance, in electricity and magnetism, gives you directions that you can use in those problems that make them make a little bit more sense. So hopefully this all helped you. I'm going to sort of slowly move this by so in case anybody missed anything, they can pause it at any point and then look back at the equation. Because a lot of stuff went on there. Over here, notice I got all that. And then I went over here and calculated the volume of a cylinder. Got kind of messy, did some scribbles there. That's pretty awesome. All right, well, I hope that helped. Have a good day.